Uh, okay, let me check the attendance. Raymond Kui. Raymond Kui, 20. Raymond Kui, 20. Raymond Kui, 20. Raymond Kui, 20. Adin Agana, 15. Adin Agana, 15. Adin Agana, 15. Adin Agana, 15. Nur Mohammed Berabedikov, 17. Nur Mohammed Berabedikov, 17. Nur Mohammed Berabedikov, 17. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Mohammed Syed Dema, 34. Masudu Zaman,
Yes,
5.
sir.
Okay. Ibrahim Rob Job, 29.
Yes, Lao Shi, I'm here.
Okay. Mikhail M. Safa, 5. Mikhail M. Safa, 5. Mikhail M. Safa, 5.
Actually, you forgot my name. It's 30.
You are,
The ID 30.
oh yeah, Mohammed Temakir, right?
Yeah.
Okay, yeah. Just to you, okay. Solomon Carlton, 6.
Yeah.
Okay. Sador Dadajonov, 8. Sador Dadajonov, 8. Sador Dadajonov, 8. Tamar Marik Daminov, 10. Tamar Marik Daminov, 10. Tamar Marik Daminov, 10.
The shadow is here. Please check the chat window.
Safa? Hello?
Please check chat box.
Hello? Who are you? Sador, okay. You are Sador, right? Sador,
I had problem with the microphone. How I fix it?
okay. Sador Dajonov, okay, I see you. Okay. I see. Let me say, yeah. Oh, yeah, Sador, yeah, I see you in the list. Right. Okay. Christ David Georg All.
Yes,
12.
sir.
Okay. Ashibu Rahman Noor, 14.
Yes, Lao Shi, I'm
Ashibu,
here.
okay. Mehrab Hossein, 15.
Yes, Lao Shi, I'm here.
Okay. Gentle Fetus, 21. Gentle Fetus, 21. Gentle Fetus, 21. Abraham K. Kromas, 22. Abraham K. Kromas, 22. Abraham K. Kromas, 22. B. Theophilus G. Russell, 25. B. Theophilus G. Russell, 25. B. Theophilus G. Russell, 25. Solomon Carleton, sorry, Solomon K. Sawyer, 26.
Yes, 老师。
Okay. Beckham Terawan Mamo, 29.
Yes, 老师。
Okay. Next, Laikun Asifa, 30. Next, Laikun Asifa, 30. Next, Laikun Asifa, 30. Next, Laikun Asifa, 30. Valery Butuk, 31. Valery Butuk, 31. Valery Butuk, 31. Valery Butuk, 31. Anna Akulova, 32. Anna Akulova, 32. Okay. Lawan Tabaco, Gabriel Marin, 33.
Yes.
Okay. Big Noir Ikram, 34. Big Noir Ikram, 34. Big Noir Ikram, 34. Azmat Haimlin, 36. Azmat Haimlin, 36. Azmat Haimlin, 36. Okay. It's attendance. Okay, let me share the slides. Okay, can you see the slides?
Yes,
Yes,
老
老师。
师。
Okay, let's start. Okay, so firstly, let's have a brief review about our last lecture. So in last lecture, we continue to discuss the compilation process in the embedded Linux. So we discussed the linker script. So here the linker script is a script to guide the compiler how to link multiple object file and library together. So if you want to check the currently used linker script, you can use the command linux ld and use the option verbose. So generally speaking, we can use the default linker script for the compiler. Of course, if you are expert on this area and you have the needed you have the need to build a linker script by yourself, and you can write one by your own. For instance, here, the linker script is a file with a postfix LMDS. So here we can see this is a simple script which goal is to determine the text section, data section, PSS, okay, their starting address. Let's say the English script. So its first line, okay, determine which architecture the bytecode, okay, the instruction set should follow to. So we know that here, okay, we are using the ARM Linux GCC, okay, as the compiler, okay. So here, of course, the output bytecodes architecture should be ARM. So here, output arc, okay, this is ARM. Then, okay, for the goal of the link script is to determine the three sections starting address. So we see that okay, here is the .text, .data, and .bss. So in this script, okay, the .text, okay, we see that there is a instruction, okay, that is to start from the address 1 0 0 0 0 0. Okay. Then the data, okay, and the BSS, okay, they are starting with the 8 8 8 8 0 0 0 0. Okay. And here we determine that the .bss, okay, this section should follow the data section. Okay. So we know that the data section stores the initialized global variable and static variables, while the .bss, this section, it stores the non-initialized global variable and static variables. While .text, okay, it stores the readable only, okay, instructions. So here, okay, it can also determine the sequence of the segment within the object file. Okay, it will be compiled to. Okay. So how to use a link script? If we just want to use the default link script, of course, you did not do anything. Okay. But if you really want to use your own link script during the linking, then you need to use ARM Linux LD, this command. Okay. And here we see that okay, -o, okay, option. Then we want to generate the executable, okay, ESP2. While the two object file here, hello.o and main.o, okay. Then -t here is to determine the link script, which one to use. Okay, here is section.ldms. Okay. Then here -map, okay, is to output the section mapping, okay, of the ESP2, okay, to the map.txt. So this is how to use the link script by your own. Now in last section, okay, we also discussed the debugger, okay, in the ARM Linux GCC system. So in ARM Linux GCC system, okay, we also use the GDB. Okay. Of course, GDB is the GNU systems debugger. Okay, not only for the ARM Linux GCC, okay, because the ARM Linux GCC is the part of the GNU system. The GDB itself, okay, is a command line model debugger. Okay, it has different various functions such as set breakpoints, single-step execution, watch variables value, modify variables value, and so on. Okay. In last lecture, okay, we discussed how to use GDB to for the different functions and show an example, show a simple example. Okay, use GDB with an example program. Okay. In general speaking, it is like the debuggers in your IDE, like the Visual Studio and so on, but it is in the command line model. In last lecture, okay, we also discussed the make. The make tool, okay, is a very useful tool, okay, for compilation, okay, in a large scale project in the Linux or Unix environment. We know that, okay, to compile these source files, we usually use GCC command. But we know that if the project is complex and consists of hundreds of source files, then we need to use so many GCC commands, and it is very boring and error-prone. So the Unix, obviously the Linux system, okay, it provides the make tools for us to compile the complex project. Also, it has the benefit that it can automatically recognize, okay, which part should be compiled based on whether they are modified. Actually, determining on the date, okay, on the date of the source file, compare the date of the source file with the generated object file. Okay. If the compiler say that okay, this source file's last modified date is later than the generated object file, okay, then it will compile, will consider these source files as modified and will compile them. Okay. Also, okay, if a header file is modified, then the source file that used this the certain header file should be compiled. Okay, if we use the make. So how the make can guide the compiler to compile the project? Okay, so it relies on a file called the make file. So the make file, okay, it essentially consists of rules. So each rules describes a target file. Okay, this target file, okay, including the dependent files and the modules, okay, and the command and to generate and update the target file, okay, like that. Okay. So the format of these rules, okay, for you will know that rule is the basic unit of the make file. Okay. So the basic format is that, okay, firstly the targets, then the comma, okay, then the space, okay, and pre-request files, okay, semicolon commands, okay, table command and so on. So let's take this one as an example, okay. So this one is to generate the test.o, okay. Then its dependency is it needs the test.c and the test.h, okay. So they need these two source files, and we know that okay, since test.h is a header file, so in the GCC command, okay, we don't need to include this. We just use test.c, okay. Here -c, okay, this option is to generate the source code to the object file, while -g, okay, is what it actually read to the GDB, okay, means that after the compilation, okay, this test.o, okay, will store the necessary information, okay, for the GDB, okay. Otherwise, okay, if we do not include the -g in the compilation commands, okay, the generated executable cannot be debugged by the GDB. GDB need the necessary information so that it can do the debugging. Okay. Also, we show an example. Okay. So this is a simple object, a simple project. Okay. We see that okay, in this project, there exists main.cpp, point.cpp, square.cpp. Okay, these three source files. Okay, and also two header files, point.h and square.h. Okay. So firstly, okay, we see the make file. Okay, because this is C++. So the compiler, okay, we need here is just an example, okay, not for the ARM Linux, okay, but this is a general case. So that okay, the compiler okay, we need to use is G++. Okay, of course, if we want to use the makefile okay for an embedded Linux project, then usually this CC here, the compiler here is ARM minus Linux minus GCC. Okay. Then the C flags, okay, minus or minus G, okay, it means to compile all and to generate the necessary information for the TDB. Then we see that main, okay, we know that to generate the final executable, okay, main, we need the it depends on the main.o, point.o, and the square.o. Okay. So this one, okay, we say that this is the target, okay. Then this is the prerequisite files, okay. Okay, then this is the command, okay. Then this is a variable, okay. We discussed what is a variable, okay, in the makefile, okay. So this is a variable, CC, okay. So essentially, the variables, okay, here is like the macro, okay, like the macro in the C programming language, okay. So essentially here, this one equals to GCC, and this one equals to okay, these options. Then we see that in this command, okay, to generate how to generate the main, okay, it use this command, okay, to generate the main. Okay, we see that -o main, main.o, point.o, and square.o. Okay, that means that use these three objects together, okay, we can compile an executable main. Then main.o, how to generate that? Okay, then we say that it depends on the main.cpp. Okay, because the main CPP, okay, it uses point.h and square.h. Okay, so okay, we say that the prerequisite files okay, include the main.cpp, point.h, square.h, and so on. Okay, like that. Okay. Then let's say some new content. Today, okay, we will discuss the embedded Linux architecture. More specifically, okay, we will see more details about the Linux system. In Linux system, the most important component is kernel. Okay, so we will discuss it from two different perspectives. Firstly, from a functional perspective. Secondly, from a source code perspective. So here, let's firstly discuss the Linux kernel from the functional perspective. So we know that Linux kernel, to some extent, okay, we can consider that it is like the Linux OS, but not the entire OS. It is the core part. It has the core functionalities of the entire Linux system. Okay. So let's say where is the Linux kernel? Okay. We see that okay, it is on the top of the hardware, while the user space things okay are on the top of the Linux kernel. So okay, we can see that just on top of the hardware, okay, in the Linux kernel, it is the arc-dependent code. Okay, so which means that okay, it depends on the architecture of the hardware. Okay, so this piece of code okay is specifically for the certain hardware of a certain architecture. Then we see that okay, the drivers and the dynamic modules. We know that okay, the drivers okay, they are used to operate on the hardware, okay, and also okay, it actually provides some functionality interface to the Linux kernel. While in the middle, okay, you see that the Linux kernel has various functionalities such as process management, IPC. Okay, you know what is IPC, right? Inter-process communication. Okay, virtual file system, memory management, network subsystem, and SE Linux. Okay, SE Linux. Okay, here is stands for the secure Linux. Okay. Also, okay, APP ARM. Okay, so this part is for the security purpose. Then we see that the Linux kernel, okay, it provides an interface to the user level applications. So usually it is called the system call interface. So if the user level application okay, want to use the service provided by the system, okay, you need to use the system calls. Of course, all the system calls are documented, okay. So the programmers can simply follow the documents and invoke these system calls. Okay. So in general speaking, okay, the system call layer, okay, it provides a set of standard system call functions for user space to access the Linux kernel. Okay. It like a bridge, okay, so between the user space and the kernel space. Why it needed? Okay. Why the system call is needed? Okay. It is because that each user level program, okay, whatever okay it want to do, okay, it have to use the hardware. Okay. For instance, okay, the simplest hello world, okay, hello world program, okay, it just to output a line of characters, okay, hello world, right, okay, to the monitor. However, how to display the characters on the monitor? Okay, so it actually okay need to use the hardware, right? The monitor. Also, okay, how to pass the output okay from the memory. Okay, we know that when the program okay, is running, okay, it is residing in the memory. Okay, then the output should be passed from the memory okay to the monitor. Okay, it should go through the bus, right? Okay, so all these things are involved with hardware. Okay, when it involves hardware, okay, of course, each hardware has its own driver, but usually the user level application it cannot directly use a device driver. Okay, so it have to go through the system kernel okay, to use it. So here, okay, the Linux kernel provides the system call interface. So when we type in the printf, so after compiler compile it, it will become the system call invocation to finally direct to the display in the monitor. So exactly what is a system call? The definition. The system call is a procedure that provides the interface between a process and the operating system. It is the way by which a computer program requires a service from the kernel of the operating system. So when a user level program make a system call, it will involve something called the privilege transformation. So we know that during the running of a program, so we know that we are currently in the space of that program. But if this program during its execution, it invokes a system call, then actually now the control will not at the hand of that program. It will be transferred to the Linux kernel. Actually, it transfers the control from the unprivileged user model to the privileged kernel model. We know that the user model it can access the limited resources within the system, but for the kernel model, since it has the root privilege, it can access all the resources, including all the hardwares. Of course, the details of the control transfer, it vary from the architecture to architecture. Usually, this control transfer, taken care of by the libraries. So the libraries actually collects the system call arguments, and if necessary, arranging those arguments in the special form necessary to make the system call. So in general speaking, in the hello world example, we know that the printf is a function from the C standard library. So how to use the display or use the monitor is actually the work of the C libraries. We don't, the details actually are hide from the program. But for us, since we are the computer science student, we should know the things behind this piece of code. Generally speaking, the system calls according to their functionalities, they can be divided into 5 categories, including the process control, file management, device management, information maintenance, and communication. Let's say them one by one. So here we list the many used, frequently used system calls in these different areas. So for the process control system call, this kind of system calls performs the task of process creation, process termination, and so on. So the Linux system calls under this fork, exit, Excel, and so on. For the fork. Fork, this is system call to create a new process in the Linux environment. Here, please be aware about that. A new process, may be created with a fork without a new program. Why? Or what is the case? So here, this fork, we don't have to either, we know that, who invokes the system calls, it must have some caller, right? The caller itself is also a process. A very common case is that the caller process just want to create a duplicate process of itself. So with the fork. So it is the case here. It just create a clone process of itself, and do the exactly and running exactly the same program of the caller process, or we see the parent process. Of course, you can use the fork to create an entire new process. So if you create an entire new process, we know that this new process can also use a fork to create its own new process. Then it's like the tree, and the process tree, like this such hierarchy. So the fork, is almost the most widely used system calls under the process management. During the system running, there always many processes are created and terminated. Then the exit. So the exit system call is used by a program to terminate its execution. We know that if you create a process, then it should be terminated. So during the termination, the OS will reclaim all the resources that was allocated to the processes, including we know that when we create a process, the OS will allocate a piece of memory space called the process space, and also the process may open some, for instance, files or use some hardwares. Actually, the hardwares in the Linux system, they are also used in the format like the file. Actually, when it use a hardware, the operation is like to operating a new file. But here we will discuss them later. Also, the process, it may use some other resources. So, but when such as the registers, but when this process is terminated, be aware about that. Here we say it is terminated, not suspended. If a process is suspended, you know, so you have learned the operating system calls, right? So when a process is suspended, so which things of that process should be stored? Can anybody tell me? When a process is suspended, which things should be stored? so as it can be restart. So we know that when you learn about something like the process scheduling, okay, then it should then based on the algorithm, okay, the system use, okay, maybe some the current running process, okay, may have to be suspended, and a new process, okay, will be taken into the CPU to run, okay. So the previous process should be suspended, and we have to store the status of the process, right? Okay. So which kind of things should be stored? Can anyone tell me?
Using the RAM and storage, maybe. Is that what you're asking? I mean, the program will stop or will stay on wait, so that the other program could use the processor.
Yeah, of course, processor. Yeah.
So to be on suspense, I mean, on wait. It's like sleeping when you leave the PC to sleep. Similar to that.
Not exactly use the sleep. Actually, that suspend, like something like, okay, when you play a game, right? Okay, you made something that okay, you need to do, maybe you need to do your work, right? Okay, then you make a save, right? Okay, and then you exit the game, okay, and you maybe do your homework, and then when you have time, okay, you may restart the game and load the save, right? Okay, it's something like that. So here, when the process is suspended, okay. So firstly, okay, the registers, okay, the registers is currently used should be stored. Okay, we know that when a program is running, okay, it must use several registers, especially such as the program counter, okay, and also the instructions, registers, and so on. Also, okay, the resources it used, such as the files and the hardwares, okay, it related. Also, okay, it's stacks and heaps, okay, of the process. So that all these things, okay, will be stored in a certain place by the OS for the process. Okay. Actually, in a data structure called the process. Okay, if you look into the Linux kernel source code, okay, you will see a process data structure. Okay, it has certain fields to store all the things. So that, and actually all the process, okay, within the Linux system, okay, they are stored as a linked list. Okay, so next time when the previously suspended, when it's turn for the previously suspended process to run again, okay, then the OS will look and locate the node of that process and read the stored information for the process and load it to memory and create and recreate its memory, its process space so that this suspended process can be run again. Okay. So here the exit process, okay, but it actually reclaims all the resources. Okay, so this is different. Okay, once it exits, and then the process cannot be restart. It is terminated at all. Yeah, it is removed from memory entirely. Okay, so we have discussed the process creation and termination, okay, corresponding to the fork and exit process. And let's say, okay, this one, okay, is the prefix, okay, for the execute. So a new program will start execution, okay, after a call to this system call. So here, for this system call, okay, we can run a new program, okay, so that we don't have to create a process first. Okay. Any process may call the execute system call at any time. Okay, so we don't have to create a new process and to run. No. We can execute and process at any time, okay, with this system call. Okay, and okay, you may ask, okay, how about the current running program, right? Okay. Because that this program, this system call should be invoked by a running program, right? Okay. So the current running program will be immediately terminated. So the new program will start executing. Okay. But okay, the context, we know that the program, okay, is when it's running, okay, it use the registers, okay, it has the open the related source files, hardware, and so on. Okay, all these things are called the context, okay, of the process. So although okay, the executable, okay, the running executable, okay, is replaced by a new one, but okay, the context are not switched. Okay, context remains the same of the previous program. Okay, so okay, essentially, this system call, okay, can run a new program, okay, in the context, in the existing process, and also terminate at the same time, okay, it terminates the previously running program. So this is the functionality of the execute system call. Let's say the file management system calls. So this system calls, okay, handle file manipulation jobs, okay, like creating a file, okay, reading, writing a file, and so on. So the Linux system calls, okay, under this open, read, write, close. Okay. So when you learn the C++, okay, you may learn some functions, okay, related to the file operation, okay, such as fopen, okay, fread, fwrite, fclose, and so on, right? Do you know them?
Yes.
Yeah. So essentially, okay, these file functions, okay, of in the C++ or in the C program, they will essentially, okay, actually, okay, it's the task of the C standard libraries, okay. When you use, for instance, when you use fopen, okay, in your program, okay, then okay, we know that fopen is a library function within the C standard library. And if you really take a look at the source code of the fopen, okay, you will see in the library function fopen, okay, it will use the open system call. Okay. but with slightly different parameters. Okay, you pass to the fopen. So essentially, okay, all the library functions, okay, they will finally use one or more, okay, system calls to fulfill, okay, its functionality. So that the user level applications, okay, when it's running, okay, unless it does not use any libraries at all, but you can think that, okay, if a program, a C program or C++ program, if this program does not use any libraries at all, okay, I think that it almost can do nothing, right? Okay. Or it will have to use this system call by itself. Okay. If the program does not use any system call and also it does not use any libraries, actually, okay, no, it can do nothing. So even it is a user level program, when it is running, okay, it also involves many control transfer, okay, because that at the behind of the execution, okay, the library has to invoke the system calls, which will involves with the control transfer from the user space, okay, to the kernel space. And let's say this system calls. So open, okay. So this is the system call to open a file. Yeah. The open system call, okay, just open the file. Yeah. To perform the operations as read and write. Okay. So we need to execute different system call, okay, to perform the operations. Okay. Of course, if by providing different parameters to the open, okay, you can decide it, okay, the mode to open a file, okay, such as you can open a file, okay, read only or write only, or read, or both can both read and write. Okay, that depends. Okay, so of course, the how to use it, we can also check the document of the open. All these system calls, okay, the Linux system has complementary, okay, documents for all the system calls. Okay, if you want to check the usage of them, okay, you can see the details in the system call documents. Then the read, okay. Then the read, okay, this system call can open the file, okay, in the reading mode, okay, so read-only mode, okay. So we cannot edit the files with this system call. So multiple processes can execute the read system call on the same file simultaneously, okay, because that this system call read open file, okay, in the read-only mode, okay, it will not change the content of the file. So multiple processes can read the same file together. Okay, either it does not involve any lock problem, right? Okay, we know that if one of the processor, okay, one process can potentially modify the content of the file, okay, then then other process when read it, okay, it may get a different result of the reading, okay. So then in this case, okay, we need the lock, okay. Of course, okay, for the lock is also a kind of system call, okay, to avoid such competition, okay. Then the write, okay. The write, okay, the system call opens the file, okay, in the writing mode. Now with this system call, okay, we can modify the content of the file. Then in this case, okay, we cannot, okay, modify, okay, the the certain file, okay, with multiple processes simultaneously. And this is reasonable, right? Okay. So once a file, okay, is writing a certain file, okay, the system will lock, okay, will lock the file, okay, until okay the current working process, okay, done its job, okay, then the next one can come to modify the file, okay, so that there will no competition, okay, between the different processes. The so-called competition is that, okay, let's say, okay, suppose, okay, all the files, okay, modify the values of the certain variable, let's say, okay, maybe just a variable, okay, counter, right? Okay, counter, okay. So maybe the process A can modify the want to increase the counter by 1, while the process 2 want to decrease the counter by decrease the counter by 1. Okay, then you can see that, okay, then the second process may want to increase the counter by 2 and so on. Then you can see that, okay, if the 3 processes, okay, are executed in a different sequence. Okay, then the fourth process, okay, if it read the content of the read the value of the counter, okay, at a different time, okay, it will get the different result, right? Okay. So the so-called competition that, okay, the multi-processes access a shared resource, such as a variable, a file, a hardware, and so on. Okay, then the execution result of a program will depend on the exact accessing sequence of these processes. Okay. So that is called competition. Okay, the competition is a problem. Okay, so that because that we want the program, okay, a certain program, okay, when it runs, we should get a certain fixed result. Okay, not a result that depends on the execution sequence. Okay, then the close. Okay, this close. Okay, we know that when we program do the programming, okay, if we use the fopen to open a file, okay, then before then after we finish using that file, we need to use fopen, okay, to close the file, okay. So here the fopen, okay, actually will use the close system call to close the opened file. The device management system call. So the device management, okay, it does the job of device manipulation, like the reading from device buffer, writing to device buffer, and so on. So in a Linux system, okay, the system call under this is the IOCTL. So here, the IOCTL refers to, okay, input and output control. CTL control refers to control, while the IO, okay, refers to input and output. So IOCTL, okay, this system call, okay, it is a system call for device-specific input and output operations and other operations which cannot be expressed by regular system calls. Okay. Of course, okay. Here the IOCTL, okay, this system call is usually it is very complex. Okay, if you check the document, you will say, okay, oh, it has several. It has a lot list of parameters to use, and the usage is really complex. Okay. But anyway, okay, still, remember one thing, okay. In the Linux system, especially okay, in the embedded Linux system, okay, if we want to operate the device, okay, essentially, okay, we actually write something to the buffer of the device, and we want to get something back from the device. Okay. So the so-called buffer, okay, what is buffer? Okay, it's like, for instance, remember the LED example we discussed in our previous lectures. Okay, how can we manipulate the LED device? Okay, anybody remember that? How can we manipulate the LED? Anybody remember? No. Nobody remember? Okay. So in that LED example, right? Okay, we want to make the LED we want to light up the LED. Okay, how? Okay. Essentially, we need to write something to the register of the LED. Okay, so we set the certain bits of the register of LED through its LED through the LED's device driver. So essentially, how to manipulate that? Okay, so it is we put something in its buffer. Okay, so its registers. Then the LED will do the certain operation. Also, okay, we can we may get something back from the device output. Okay. For instance, a printer, right? Of course, we know that the printer will print something to the paper, right? Okay. Actually, before it print to the paper, okay, it actually output the needed things to its own buffer. Okay, so this is also an example that we can get something back from the buffer of the device. So come back to the IOCTL. For the IOCTL, okay, the parameters among it very important is that where what is the handle of the device? Okay, then what is the buffer? Okay, what is the buffer of the device? Okay, then you want to read from the buffer or write something to the buffer. If you want to write something from buffer, okay, then which means that okay, you want the corresponding hardware, okay, and to do certain operations. Then after that, okay, you may need to use the IOCTL, okay, to read the result from the buffer of the device. Okay. So this is the usage of IOCTL. Right? It's a little bit complex. You just know it, and that's okay. Okay. Then the information maintenance system call. So what is information maintenance? Okay. Actually, okay, this piece of system calls handle the information and its transfer between the OS and the US program. In addition, okay, OS keeps the information about all its processes and the system calls that are used to access this information. The system calls under these categories includes the get PID, alarm, sleep. For the get PID, so in the Linux system, okay, so we know that in the Windows system, have you I think you have used the task manager, right? Anybody have used the task manager in the Windows system? Task manager? No?
Yes.
Yeah, okay. So when you use the task manager, okay, you will, when you open the task manager, you will see a lot of program are running, right? Okay.
Yeah.
So have you see the details of the running program in the task manager?
Yes, sometimes.
Okay. Then you may see that in one field of the program information, okay, it actually has its ID, right? Okay.
Yeah.
So it is so actually not only in Windows but also in other system. Okay. So once a process is created, it will be attached with a unique ID. Okay. So it is called the process ID. Okay. It is unique, the unique number to represent that process. So here the get PID, okay, is to get the process ID of a certain process. This function, okay, this system call should always be successful. Okay, and it always because for exist process, okay, for existing process, okay, for a running process, it must have a PID. The pure process ID in Linux is short for the PID. Okay. Then alarm. Okay. This alarm, okay, actually like the alarm in our daily life. Okay. But here, okay, it sets alarm clock, okay, for the delivery of a signal, and when it has to be reached. So it arranges for a signal to be delivered to a calling process. Okay. So okay, this one is related to the sleep. So sleep function, okay, of sleep system call. Okay, what does it do? Okay. It suspended the execution of the current running process for some interval of time. Okay. So actually in the C program, okay, it also has the sleep function, right? Actually, they have the same, almost the same functionality. Okay. So during the sleep, okay, means that now the process, okay, is suspended. Okay. Then during this interval, other process can execute. Okay, but how? Okay, but how the process to be resumed? Okay, at a certain time. Okay, then okay, we will use the alarm. Okay, so the sleep alarm, right? Okay, we want to wake up. Okay, we will set up an alarm, right? Then in the operating system, we have a similar case. Okay. So we set up alarm, okay, to send a signal to the previously suspended process to wake it up. Okay. But of course, even when the process is wake up, okay, but and resumed, but it depends on the process scheduling algorithm. It might still have to stay on the waiting list. Okay, it kind of not to say that okay when it is resumed, it can be directly sent to the CPU to run. No, okay, usually it still have to wait until the scheduler, okay, to schedule a new chance for it to be executed. So the alarm and the sleep are usually used together. so sleep for a certain time, okay, then at a certain condition, yeah, for instance, after a certain time elapsed, okay, then we use alarm, okay, to try to resume that process. So these two are used together. Okay, well, then how about PID? Okay, then the PID, okay, is a process, okay, to be slept, to be alarmed, okay, that used as one of the parameter, okay, of these two, okay, system call. Right, then the communication, okay, communication system call. Okay, just one question. Do you know IPC, the inter-process communication? IPC, inter-process communication. Do you know it? No?
What
Okay.
was this? Sorry.
Hello? Inter-process, Lavan? Okay.
PC, yeah.
So you know the inter-process communication, right?
Yeah.
Okay. So can you just tell me something about it?
When programs communicate with each other within the operating system, maybe to share the storage or to take the address, or what was the process? Yeah, the processor when they're taking time using the scheduling algorithm. So they need to communicate. So that I think that's why they use it.
Yes, definitely correct. Yeah. So in many cases, okay, the two processes, okay, because that, for instance, okay, they want to cooperate together, okay, they need to communicate with each other. Okay. So generally speaking, there are two models are used for the IPC, inter-process communication. The first one, okay, is the message passing. Okay. So for instance, like the email, okay, you know that so the two process, okay, exchange the messages with one another. Okay. Another one is okay, you just mentioned, okay, they communicate using a piece of shared memory. Okay. So they put the message, okay, to be communicated, okay, in the shared memory, okay, so that the two process can see each other. So for the two models of the IPC, okay, the related system calls, okay, include under this are the pipe, share memory get, okay, and map. So the first one, pipe, okay, the pipe, okay, is a widely used system call for the process communication, okay, in the Linux system. So pipe, okay, it actually create a pipe data structure. So we know the pipe in our daily life, right? Okay. Actually, it create something data structure like the queue, okay, like the queue, message queue, essentially message queue, okay, between two process to be communicated, okay. So then is two of course, okay. Then to communicate with pipe, okay, we need also provide different different settings of that, okay, such as the port and something, okay. Then the two process can use the data structure for communication with the pipe system call. Well, the SHM get, okay, this one is for the second model, okay, the IPC, okay, through the shared memory. So because you can see the name, right? And this one stands for the shared memory segment. Okay. So it is mainly used for the shared memory communication. So this system call is used to access the shared memory and access the messages in order to communicate with the process. So here, the shared memory. Okay. This one is interesting because that we know that the process, okay, each process has its own address space, right? Okay, so it can access the memory within that space address space. Okay. But it cannot usually it cannot access the memory key within another process. It's not. Okay. So that it can, so which means that a process cannot directly read something from another process. So that's why we need the shared, okay, the shared memory. Okay. One simple case is that, okay, the process A, okay, for instance, the process A and the process B want to communicate with each other, okay. Then the process A can ask the operating system to allocate a certain piece of memory, okay, also still within its memory space, okay. But this piece of memory space, okay, as a shared memory, which means that it can be viewed, okay, it is visible, okay, to the process B and can be accessed by the process B. Okay, this is one common case. Of course, okay, this shared memory can be out of the address space of the two processes. But that thing is very complex. We do not discuss it here. Okay, and then map. So this function is used to map or unmap files or device into memory. So essentially, this system call is responsible for mapping the content of the file, okay, to the virtual memory space of the process. Do you know what is virtual memory? Anyone? I think you should know what is virtual memory, right? Let me pick up one. Okay, Sador, are you here? Sador. Okay, do you know what is virtual memory?
Virtual memory.
Virtual memory.
Virtual memory, right?
Yeah, virtual memory here. Just the things we, just the term here, virtual memory.
Oh. Yeah, is it similar like the normal memory, but used as a when you don't have a free space, like when the operating system doesn't have enough space, it uses the virtual memory as a compensation.
Yes, continue.
The virtual memory is a storage allocation scheme in which secondary memory can be addressed as though it were part of the main memory.
Yeah, generally you are right. Okay, so when we need the virtual memory, okay, it is because that sometimes, okay, the physical memory, okay, is not enough, okay, for the program for the system to run. Okay, so actually in this case, we can use, okay, some, for instance, okay, the space on the hard disk to use it as part of the memory. Okay, So to combine them together, okay, we use the virtual memory. Okay, so actually, okay, in most of cases, okay, when we run a program, okay, or we see the process, okay, the so-called memory access, okay, it usually refers to the access of the virtual memory. Okay. So here is mmap, okay, used to map, okay, the executed files, okay, or the device to the virtual memory, not the physical memory. Okay, the physical how to map the virtual memory to the physical memory. Okay, it is the job of the MMU, okay, memory management unit. Okay, so that's not the case, not the job of the mmap. Okay. So when we say the mapping, map the files to the memory, okay, is okay, easy to understand. But how device, okay, is because that in the Linux system or in the Unix system, okay, obviously in the Unix style system, they also view a device as a file. Okay, so for instance, you want to launch a device, okay, you need to use the open system call. Then if you want to, okay, send something to a device, you need to use the write system call. Okay, and you want to get something, get some output of the device back to the memory. Okay, then you can use the read system call. So essentially, the operations to a certain device, okay, is like the something, okay, we done for a certain file. Okay, so the map is to map it to the memory so that we can do these operations. While the unmap, okay, the unmap is that okay, we delete, we remove them from the memory space. Okay, so let's come back to this figure. Okay, so we have discussed all these a bunch of system calls. Okay, then let's see look into details of the each functionalities of the kernel. Okay. So for the process management, okay, so we know that okay, it is supported okay by this for instance process creation, we can use a fork. Okay, and after that we use the execute. Okay, then terminate. Okay, we can use the kill command, and also we can use the exit system call. While for the IPC, okay, then we can use the pipe. Okay, for the communication, and we can use the shared memory for the communication. Also, okay, the kernel will charging for the process scheduling. So which means that there are multiple processes. Okay, so which process should be put into the CPU to run? Okay, it depends on the schedule. We know that the easiest schedule algorithm okay, is the FIF, first in first out, right? And also some complex, okay, more complex scheduling like the round robin and so on. Okay. It depends. You can the system in a kernel. Okay, you can determine the algorithm you want to do. Okay, but in a Linux, okay, the default, okay, by default the process scheduling algorithm is a round robin. Then the memory management. Okay, the memory management, okay, is essential. Okay, because that only when a process okay, of our device is mapped to the memory, okay, then we can access and use it. Okay, so but especially when come to the Linux, okay, we can say that the success of Linux okay, is closely related to its excellent memory management. Okay. Because that okay, the efficiency and the stability of an operating system okay, often depends on its memory management mechanism. Okay. So for instance, okay, if you use some early version of Windows system, okay, you may meet some problem like called the blue screen. Okay, when the blue screen happens, we see that okay, we see some memory dump and so on. Anyway, so this is because that in the early version of the Windows system, memory management usually has something bugs, so that when the operating system and some big program are running together, okay, in that operating system, okay, some big programs running together, okay, usually it will got something wrong like the memory leak and so on, and cause the entire system to crash. Okay, so actually memory management is very important for the entire OS. Yeah. So here, okay, that's why we need to have the virtual memory, okay, because that we for every program, okay, we want to have the infinite amount of the fast memory, okay, but of course it is not possible. To do so, okay, to solve the problem of infinity, okay, in Linux system, okay, it introduces the virtual memory. Also, okay, to solve the problem of speed in the Linux system, introduce the cache. Yeah, we know that okay, the cache speed is just almost the same as the CPU, okay, and it is faster than the main memory. But we know that here the cache, okay, it's usually has a very small size. Okay? It's not as big as the main memory. Okay, so only the important things can be used in needed things are running in the cache. Okay, while the main things are stored in the main memory. Okay? So as a result, the capacity of the game, and so this memory hierarchy, I think you know that in the operating system calls, right? Okay. So the capacity of memory is close to the hard disk, while the speed of the memory is close to cache. The network protocol stack. So the kernel protocol stack provides rich network protocol implement for Linux. Okay. Usually, the most important protocol stack in the Linux system is the TCP/IP. Okay. So this protocol provides the most efficient and concise implementation, okay, for the in all OS, okay, for the network. While the virtual file system, okay, so the so-called virtual file system, okay, is something like something to hide the details of the virus file system, okay, because that the real file system are different, such as in Linux system, we can have the EST, GFS, XFS, and so on. Okay, but the application don't want to program for a certain kind of file system. So the VFS actually provide a general interface for the user level application and hide the details of the different file system. Device driver. Okay, so here we have discussed the device driver for several times. So actually, in the Linux kernel, most of the code, okay, actually are stored in the device driver, okay, because that there are a lot of hardware to be operated, okay, and the underlying hardwares, okay, have to be used by the device driver. Then the interrupt management system. Okay. So this one is the cornerstone of the computer operation, okay? Because that, for instance, for the system call use, okay, how the control is transferred from user space to the kernel space, okay, it depends on the interrupt. So it is a readable and efficient hardware and software response mechanism, okay, that is established to the underlying hardware interrupt system of the process. So we have the hardware interrupt and the software interrupt. Okay. Let's stop here today. See you next time. Bye-bye.
See you, Loshi.